Good morning, everyone. Welcome to the fourth installment of Crane Engineering's Virtual Tech Tour series. This morning, we're going to be getting into some of the key principles of precision repair on rotating equipment. I'm Dustin Wietoff, the Vice President of Sales at Crane, and I really appreciate you all taking some time to spend the morning with us. And hopefully, y'all take away a few things that'll help you improve the quality of your repairs, ultimately extending the mean time between failure and overall reliability of your equipment you're operating in your plants. Before we get into the training this morning, I did just have a few housekeeping items to cover. We do have quite a few videos throughout this training session this morning, and the audio does work better through the computer. So if you're not already using your computer audio, highly recommend making that change from your phone to your computer if possible. If you do have questions as we're moving throughout the presentation, please feel free to enter those in the questions box, and we'll be sure to save some time at the end to get to as many questions as possible. If we run out of time and don't have time to get to one of your questions, we'll certainly follow up and make sure that that gets addressed. Pretty important, please remember to complete the survey at the completion of the training. So when we end the session, a survey will automatically pop up, but you should receive one within 24 hours via email as well if you don't have time to complete right after the presentation. Important for a couple reasons. Number one, we'd like to hear from you about how we're doing and ways we can possibly improve, and topics you might like to hear about in the future. Also, if you applied for DNR or professional development credits, the survey will be required to receive those. We got to have your information to make sure we can get you your credits. And then also there will be a chance to win a free troubleshooting package, which I'll talk about a little bit more in a minute. We will have some interactive poll questions as we're moving throughout the training, so definitely would appreciate your participation in those. And then lastly, just a reminder that a recording of this presentation will be made available upon its completion. So if you want to use it for future reference or have others in your organization that you think could benefit, please feel free to share. I mentioned the pump troubleshooting package. You'll have a chance to win, so you can opt in for a drawing for this package on the survey. So it consists of a couple wireless vibration and temperature sensors, also pressure and temperature sensors for the process piping itself, so we can look at what's going on in the suction and discharge side of a pump. And then a couple visits from our team to install the sensors, review the installation, equipment history, those types of things, and then to come back and collect the data and provide an RCFA on what we think is going on. For our presenters this morning, I'm pleased to announce that we have John Geiger. John is a mechanical engineer with over 30 years of experience in maintenance and engineering and process plants, and he's been with Crane Engineering as our service manager for the last 5 years. And then we also have Rob Adair. Rob is formerly the owner of Rapids Process Equipment. RPE was the rotating equipment repair shop we acquired in late 2020. And Rob also brings a significant amount of experience in rotating equipment repair. So happy to have those guys with us this morning. And before I turn it over to John and Rob, we will get into our first polling question. Just test that out for a second here and make sure you're all with us. So the question this morning is, what brings you to the tech tour today? So are you here just for the credits? Here to improve your overall just general knowledge of rotating equipment repair, or are you currently having an issue with some repairs that might be moving through your shop at this time? So we'll give you just a few seconds here to answer that question. Yeah, we'll go ahead and close it. All right, so looks like a few of you are here just for the credits, which is totally fine, but most of you are here to improve your general knowledge of rotating equipment repairs. So fantastic, we appreciate that. And without further ado, I'll hand it over to John Geiger.
All right, well, we've got a lot to go through, so let's get right into it. So today's discussion, we're going to be focused on the topic of precision repair. So our discussion will be focused on pumps, but it's important to remember all the principles that we're going to review today. They apply to precision repair of really any type of rotating equipment. So precision rebuild, what does that mean? Two things. We can talk about practices. First off, when we talk about practices, this type of tool, the big hammer, generally not a precision tool. Rather, a tool like this, a micrometer, this we would consider a precision tool. So we talk about an example. Let's say you're assembling a new gear, you have a new shaft, and things just are not fitting together just right. So taking out that big hammer and beating them together, that's, like I said, not a precision practice. But if you take those gear and that shaft, take a close look at them, verify some measurements, take some precision measurements with a micrometer, make sure things are correct, maybe use a flat file to remove some burrs, and then if you retry until everything goes together smoothly, that'd be considered precision practice. And second, let's have the right attitude. So you need to have a questioning attitude, an attention to detail attitude. When you're not sure, you should stop, research, use all your available resources to find the correct answer. Generally, the Nike slogan of just do it, that attitude doesn't apply to a precision rebuild. And of course, the goal is equipment reliability. So our discussion will be focused on pumps. Pumps come in all shapes and sizes. Here we have a large vertical turbine pump. This is a rotating assembly for a double suction centrifugal pump, split case pump. Progressive cavity pump. And here's a few end suction, medium consistency pumps, which we rebuilt. So the precision principles, they apply to all these different types of pumps, and as mentioned before, really to all rotating equipment. So during our presentation, we'll spend time reviewing these principles with a simple ANSI end suction pump, and in this case, a Gould's Model 3196. So just do a quick review of some of the pump terminology. This would be the pump casing, the impeller, stuffing box, mechanical seal, frame adapter, and then the power end. We'll start out talking about the power end, and the power end is really the mechanical heart of the pump. The components we can see over there on the left, obviously in the middle, this is the shaft. Over on the left-hand side, there is the thrust bearing assembly. Over on the other side, the radial bearing. We have a bearing frame, which is housing the radial bearing, and a thrust bearing housing. And then on each side, we'd have oil seals. So the design of the power end, it's very similar to the mechanical workings of really many rotating equipment designs. So our service engineer, Josh, he's going to give us an introduction into the power end precision rebuild.
In front of us here, we have a standard power end assembly from a standard end suction centrifugal pump, specifically a Gould's 3196, commonly found in the pulp and paper industry. This one has been modified slightly for easy disassembly for demonstration purposes. The power end assembly consists of a few different components. The main being the bearing frame, which contains the lubricant used to keep the bearings lubricated, whether that's grease or oil. It would also consist of the shaft that the bearings are mounted on, the bearings themselves, both thrust and radial, the sealing device, which could be oil seals, lip seals, or a labyrinth seal to keep the oil contained in the bearing frame, and the thrust bearing housing, which would mount to the rear side of the bearing frame. Here. Although disassembly and rebuild at this point would look very simple, there are many details that need to be adhered to, and precision is key. Although many facilities at this point would see a pump rebuild as something as simple as putting new bearings on a shaft, there's much more that goes into a precision rebuild and much more that we look for during our inspections. Some of those key items are the bearing fits. There are 4 bearing fits in total on a pump. One is in the bearing frame, the second in the thrust housing, and 2 bearing landings on the shaft where the bearings are mounted. Making sure that these bearing fits are within tolerance is key and critical to a quality pump rebuild and ensuring the longevity of your pump. The next item that we look for is the shaft quality and condition. There are a few items that we check during this inspection, and one is being the shaft runout. We want to make sure that there's no runout in the shaft, it's not bent, it's as straight as can be. There's sometimes some damage to the shaft as well. In the lip seal areas, there can be lip seal grooving, which would allow a leak path for the oil to come out of the bearing frame. And there could also be damage at the packing location if the packing has been over tightened and running too long like that. The next item that we make sure we do during a rebuild is we use quality tier 1 bearings in our rebuilds. This is also key to ensuring the longevity of your pump. You get what you pay for. Another important part to ensuring a quality rebuild is ensuring you're using the right tools. An example of this is a bearing heater that we use before we mount the bearings on the shaft. Throughout the reassembly process, we also go through many quality checks. An example of this is once the pump is reassembled, we once again check the shaft runout to ensure it is square and true to the bearing frame. We also check all of the torques of every bolt on the frame to ensure they are to spec. Another key item that we like in our facility is a clean room. This room that we're in currently is separate from the rest of our shop to ensure that no contaminants, no particulates, and no debris will be thrown in the air and caught in the bearings during a reassembly.
All right, so let's take a deeper dive into some of the concepts that Josh introduced. First off, bearings. Why always replace the bearings? So bearings have a life. This chart is from the FAG bearing manual, and it shows that bearings do have a design life. Even with the proper care and operation, the design life could be as low as 14,000 hours. So which is equivalent to 2 years. So you never know exactly how old the bearing is or what conditions it's been subjected to. So we need to follow the philosophy of just replace, don't reuse. Another thing to talk about is bearing specification or bearing nomenclature. So I've got a bearing here. Stamped on the side of this bearing are the numbers 6310. So 6310 is the basic designation of this bearing. It explains the size and the type of the bearing. It is not, however, the full description of the bearing. As seen in above in the nomenclature chart, the basic designation is primarily just number 2 of the total description of the bearing. The important details are explained in the prefixes and suffixes to the basic designation. So the common mistake is to assume that all 6310 bearings are the same. Important details like the cage design or the internal clearance specification, those cannot just be assumed. So what makes this more difficult is that this information may not always be on the bearing itself. So the statement here on the right of the slide comes right out of the SKF bearing manual. Basically saying the full description is not always on the bearing, but it will be on the package. So obviously the original bearing box is long gone when it's time to do a rebuild. So what's the answer? I think the best answer is obviously you got to use your resources, but the OEM is usually your best resource. Also, reputable bearing suppliers normally have access to bearing engineers, and they can properly identify all the details of your bearing. So bearing fits. Back to this bearing. The bearing fits specify the dimensions and the tolerances for the shaft, in the bearing housing, which will properly hold this bearing. So the shaft, we need to have the proper interference fit on the inner race, and the outer race, we need the proper fit that will hold the outer race when this bearing is in operation. So it's important that the races do not slip either in the shaft or in the housing when the machine is running. Slipping is what will initiate bearing failure. It's a big cause of bearing failure. So adherence to bearing fit tolerances will prevent slippage, and it will maximize and optimize bearing operation and the bearing life. So as shown in this chart, there's many bearing fit classifications. So the selected fit classification that you'd use is based on the machine, its design, and its application. The majority of all pump designs, the fit classification for the shaft is a K5, right there, and the fit classification for the housing is an H6. This is for the majority of pump designs. For rotating equipment outside of the pump world, you need to determine what that proper fit classification should be. And this can be challenging. The OEM generally knows, but often be reluctant to release this design information. Sometimes it's in their manuals, sometimes not. Bearing manufacturers can also be relied upon. They provide some general design guidance for applications, but you need to do your due diligence and really determine what that proper fit classification is. So here, just show you some of the tolerances, dimensions for a shaft and bearing housing for a K5 shaft fit and an H6 housing fit for a typical bearing. You can see the tolerances are very tight. 5/10,000ths of an inch for the shaft and 1/1000th of an inch for the housing. So for precision rebuild, you need to hold to these tolerances. In the case of pumps, the shaft fit is critical to ensure no slippage of the race on the shaft, and it's critical to achieve the optimal operating internal clearance of the bearing. I'll talk a little bit more about this on the next slide. So the proper fit on the housing ensures no slippage of the outer race in the housing. Although it is a loose fit during assembly, it becomes a tighter fit when the pump is in operation and the bearing is at operating temperature. So bearing specification, the fits, the equipment design, they're all connected. So for example, the bearing I've been showing you, which we commonly use in a number of Gould's pump rebuilds, that bearing has a C3 internal clearance specification. So there is some clearance and some movement between the races and the balls. So this is one of the detailed specifications that we talked about in bearing nomenclature that's critical for the defining what that bearing is. But if you took this bearing and you just ran it at that internal clearance as it is right now, it would probably not last as long or operate as well as it should. But when we take that bearing and we install it with the proper interference fit on the shaft, and when we account for the expansions at design operating temperatures, this internal clearance will change. And the resultant operating internal clearance by design will be optimal for operation of the bearing and the overall performance of the machine. Okay, do a quick polling question related to some of our discussion on bearings. So what bearing fit classification is generally used for the shaft fit in a pump application? So you have 4 choices: H6, capital H6, J5, lowercase j, K5, lowercase k, or K5, capital K. Go ahead and submit your answers. Okay, so it looks like the majority of you got the answer right. It is a lowercase K5. And the other one's like the H6, which a number of you put down for that, capital H6, that would have been for the bearing housing. All right, let's move on. So the shaft, we can talk a little bit more about shaft inspection, and our service tech Nate, he's going to go through a precision inspection of a pump shaft.
Today we're going to inspect the Gould's JC slurry pump shaft. First thing I'm going to do is give everything a visual inspection. So starting on the coupling side, we can see where the old coupling was sitting looks okay. Either side of that coupling has some severe pitting, some severe wear, corrosion. That could be an issue if you ever wanted to swap out a coupling. And we all know good couplings equal good alignment. So that's something to take into consideration. Next, we're moving up to the lip seal landing on the thrust side, checking for any grooving, which I could just run my finger across this. I can feel wear there. So that's telling me we got some grooving. The grooving itself could possibly be repaired if the shaft was in decent condition otherwise. Next, we will look at the threads on the shaft for the lock nut, checking for any damage, burrs, etc. This shafting threads look okay. Now we're moving to the bearing landing on the thrust side, checking for any fretting or discoloration. That looks okay. Now we'll move down to the radial bearing fit, checking for the same things as we would on the thrust side. Then we'll move down to the lip seal land on the radial side, which we have some grooving here, very similar to the thrust side. And some corrosion here, right after where your lip seal lands. That right there is pretty significant. Again, could be repaired if needed. Now we're moving down to where your shaft sleeve would actually sit. And here we're noticing some really significant pitting. We're seeing some cuts from somebody running a cutoff wheel, probably to remove an old sleeve. Some of this wear is a little concerning because we all know we want to have a good shaft sleeve landing for good mechanical seal reliability and or packing. Next, we're moving to the impeller side threads, just checking them for condition, burrs, nicks, any galling. Those look okay. Now we're going to check shaft runout. Initial setup here would be my V-blocks at my bearing landings. Very critical we're not on something such as the lip seal landing, because our bearings right here. So I have my indicator set up next to my keyway, and I'm going to give my shaft a spin and watch. We are looking for 2/1000ths or less on a shaft of this size. As we can see, we have a significant dip there. So that dip could be concerning, considering this is our coupling side. And a good coupling side means good laser alignability. Next, I would come down and check the impeller sleeve, shaft sleeve side, to make sure that is within spec, because we want our mechanical seals running in tolerance. And do the same thing here, just spin it. This side has very minimal movement. So I would say the mechanical seal side of this thing, impeller side, is in okay shape. So we're gonna take some dimensional checks on the bearing fits of our shaft. First thing I'm gonna do is come over here, grab my micrometer, and verify it is set to 0 on our standard. We're zeroed out. No changes need to be done to the mic. I will log that on our sheet. that we are good, and we will go over to the shaft. So we are going to check the thrust fit on the shaft. I'm going to look at my dimension, follow my chart down, and find the spec. Right now we're at number 16 with the tolerance of 3.1502 to 3.1497. The total tolerance would be 5/10. The shaft measurement is 3.1495. So we are 2/10 undersized. The tolerance on these is extremely critical. Being under means it's out. Out is out. So we would also check the radial fit of the shaft, exactly like we did on the thrust side. This fit is also undersized. Overall, the shaft has a lot of issues going on with it. On the coupling side, we have these corrosion issues and pitting. We have lip seal grooving on the thrust end. Our thrust bearing fit is under. The radial fit is under. More lip seal grooving on the radial side. Pitting, corrosion on the shaft sleeve side. So this shaft would be no good to reuse.
All right, good job, Nate. So a couple things to note from Nate's discussion. First off, bench shafts, something with more than 2 thousandths run out. So these are going to cause vibration, bearing failure, mechanical seal failure, and a bench shaft is not a repairable condition. A little bit about bearing fits. So repairs to the shaft, generally not repairable. You know, shaft fits, they could be repaired by, there's a process where you'd chrome those fits and then grind them to a proper dimension. This solution, not always reliable, and we don't recommend it. A little bit unrelated to the shaft, go to the bearing housing, just a quick discussion on repairs of that. Bearing fit repairs to a bearing housing are possible in some cases. This could be done by sleeving the bore and machining back to the proper dimensions. Back to the shaft, impeller fits. One thing Nate didn't talk about because it didn't apply too much to this shaft, but some shafts have a more defined impeller landing area. This area requires a very tight tolerance fit. Loose fits will cause imbalance and even shaft breakage. So we're going to move on to the assembly process. We'll talk about bearing care, installation. Maintaining the integrity of your bearings is important from storage through installation. So during installation, you want to keep your work area isolated from dirty work. You want to keep your bearings packaged until just before assembly. You want to expedite the assembly process until bearings are isolated in the machine. If this isn't feasible, you need to cover the bearings with a cloth until the machine assembly can be completed. And the bearing heater is the best assembly tool. So our service tech, Paul, he's going to demonstrate some of the details associated with bearing heaters and bearing installation.
So we're going to use the bearing heater to heat up these bearings, and there's a couple things that we should know about the bearing heater. One, when we heat the bearing, we need to take the probe and put it on the inner race of the bearing so that when that reaches temperature, that the inner race expands enough to slide on the shaft. If you put it on the outside, by the time the temperature transferred from the inside to the outside, the inner race might be well over 230 degrees. So SKF recommends 230 degrees Fahrenheit, and that's what we do. We usually use the bearing heater because if we press the bearings on dry or cold, then we end up wearing that shaft away. This way it expands big enough to slide on, and then we can save the shaft. Second of all, once we reach our temperature, the bearing machine will beep. It'll tell us, one, that it's at temperature, and two, when it's beeping, it's demagnetizing the bearings so that once you put it in the pump, the metal particles won't attract to it. So it's important to let it beep a couple times to get it demagnetized and then install it on the shaft. So now that the bearing reached temperature of 230 degrees, it's beeping, demagnetizing itself. I shut it off. I take the probe and send it to the machine. Now, when you install it, you get it up on the shaft, and you get it, you know, trying to get it right around the center of it, and then we just slide it back on. Oops. And then we hold it and turn it a little bit to keep it from shrinking and coming away from the shoulder. So once it reaches, the shaft reaches the temperature, or the bearing cools down, the bearing will, now the inner race doesn't turn anymore, so we know that we got it locked where it's supposed to be. So then we let it cool down. This one happens to run on grease, so once this cools down, then I will pack it full of grease.
Okay, one more note about bearing handling and how cleanliness is important. So on this slide, this is a microscopic photo of a bearing race that failed. The failure was really started from one point defect, which is noted at point A. So this small defect, it could be some grit or some sand, or maybe just a defect caused by rough handling. But the point defect, it will grow into developing damage of the bearing race in the rolling direction of the bearing, ultimately results in bearing failure. This is also another reason why you always replace bearings and not reuse them, because you don't know what you can't see. So after power end rebuild, completion of the pump assembly requires quality checks and attention to detail of the assembly process. So these practices for a pump, they apply to assembly practices really for all rotating equipment in general. So our service tech, Kevin, he's going to review some of these practices for the Gould's 3196.
Building up a power end, replacing the shaft kit, and we'll do the as-built checks along the way. I'm just setting up now to check the end play, which is the first check we generally do, and be sure that it's in our tolerance and in our spec. And it's less than 1, which is very good. Next, I will check shaft run out off of the bearing frame. May be sure that that is in tolerance as well. And this one as well has very minimal run out, less than 1,000th. The torque is very crucial, and it is only 20 pounds of torque. The gasket is just a thin rubber membrane that without enough torque, without a proper torque, could easily come out of place and create a leak. If you over torque it, there's a small raised ridge on the flange, a small raised flange up there, and that's really the sealing area of it. If you over torque these bolts, you could cause distortion in the frame adapter itself, or some pull on the bearing frame, and or pinch or extrude this rubber seal. There again, you'd have a leak or an improper fit if you warped it. Okay, I had previously dropped it on and aligned it partially onto the pins and got the bolts started. Ran the bolts up just to snug, just to bump, so we can then come back and set the pins, which will ensure a proper lineup. Come back and verify our torques. And then I'll go around one more time. And then that spec will be noted on the build sheet. After the frame adapter has been installed, aligned, and properly torqued, we'll check the runout on the frame adapter itself. Our tolerance on this is 5.
-2. Back up to 0. -1. -2. All right, so we have 2 thousandths run out on the frame adapter, which is well within tolerance. I've slid the shaft seal on and then lubed the seals on the O-rings on the mechanical seal, slid that over the shaft sleeve to make sure I've got the alignment correct and it's positioned in the right orientation. These cartridge type mechanical seals are very, very expensive, very, very precision parts. So they really have very little tolerance for anything being out of spec. That's why our shaft tolerances, our runouts, our impeller balance, etc., is so critical to maintain the integrity of this mechanical seal and ensure its long life. So then we will take the, after the seal is just slid into place, we'll take the stuffing box and very gently slide it down to make sure that our orientation again is correct and set it into place. With the seal, mechanical seal slid over the sleeve, then I drop the stuffing box on there, aligning the bolts up with the flanges in the seal, starting the bolts and bringing the seal up, not tight, but just bring it up till it meets the stuffing box. Tighten the stuffing box down, and now we'll check the runout on the stuffing box. Well, our spec is 5 thousandths. I got about 3. About 4. And back to 0. So we've got about 4 thousandths run out on the stuffing box, which is in tolerance. So we can go ahead and continue our assembly.
Okay, a few further notes on Kevin's assembly checks. So no matter what you're rebuilding, quality checks and rechecks are critical. Critical dimensions of the new components or repaired items, they always need to be checked. It's just good quality control. Bolt torque specs. So in the case of this assembly, the frame adapter installation, torque value is normally lower than what you would normally expect. This is due to the design of the equipment. So it's important to review bolt torque specifications in equipment manuals. Assembly steps, in the case of the mechanical seal and the stuffing box assembly, if done incorrectly, the mechanical seal will prematurely fail. So it's critical to ensure mechanical seal is centered on the shaft, not necessarily in the stuffing box bore. Okay, our discussion so far has been focused on the mechanical end of the pump. So now our service and parts specialist, Joe, he's going to talk about the liquid end of the pump, or what we'd consider maybe the business end of that pump.
Today we're going to talk about the wet end components of an end suction centrifugal pump. The components are the casing or volute, the impeller, and the stuffing box cover. And over here we have a back pullout assembly with a John Crane mechanical seal. So to do a precision rebuild of these pumps, the whole expectation is to get this pump rebuilt in a condition that makes it perform like new or as close to new as absolutely possible. So to do that, we have to follow certain inspection criteria. So from the top, we'll look at the casing. So in this casing, there's certain areas that we inspect, and we're looking for grooving across the face of the casing. We're looking at the casing gasket area, looking for cracks and irregularities or washouts. And then also up inside here, I'm pointing at the cut water. So that cutwater area needs to be smooth and as straight across as possible. So as these pumps become older and older, and as we change out back pullout assemblies, the casings typically stay installed in the piping. So it's very important that we look closely at the condition of the casing when we do a precision rebuild. Okay, next we have the impeller. The impeller has a surface that mates up against the casing. And what we're looking for is grooves in the impeller or generalized wear, bent vanes, as well as the condition of the back pump out vanes. And also we look at the connecting surfaces, the threads of the impeller, and the surface where it mates up against the shaft sleeve. Now we're going to look closely at the stuffing box cover. The stuffing box cover we inspect for wear, grooves, pitting, or damage to the surface that the impeller matches up against. So any irregularities are caught. We also look at the gasketing surface that mates up against the casing, as well as the bore where the shaft sleeve goes through the stuffing box cover. So we look at all those different areas, as well as the face of the stuffing box where the mechanical seal mounts. Lastly, we look at where the mating surface would go against the frame adapter, where those mating surfaces are together. Okay, so those are the three components that we're looking at and the areas that we're looking at. So when we're looking at how deep grooves or irregularities are in the casing, those need to be 1/8 of an inch or less. When it comes to the impeller, it's even a little tighter. The wear, grooves, or irregularities to the face of the impeller have to be 1/16 of an inch or less. Any bent vanes basically eliminates this impeller from being reused. And then lastly, the back pump out vanes have a criteria where they have to be within 1/32 of an inch. And you don't want to see rounded edges from wear, from abrasion, and so forth. And then when we look at the stuffing box cover, the same criteria, grooves 1/8 of an inch or deeper, or generalized wear 1/8 of an inch. And you do this by checking with a straight edge across, and you can make a judgment call on that. But anytime you reuse components that have grooves, generalized wear, or opened up clearances, each one of these things will have an effect on overall performance, efficiency, and reliability. So the impeller is set at a clearance to this casing. And in the ops manual, it tells you on a 3196 MT of this size with a standard temperature of 200 degrees F or under, you would set this at 8 thousandths clearance. So when you're setting 8 thousandths clearance to the casing, that also allows for a clearance to the stuffing box. When you add these two clearances together, you typically will have 60 to 85 thousandths total clearance from the casing to the stuffing box. So as you have wear to these components, the performance and hydraulic operation of this pump will fall off. So you can reset the impeller clearance to the casing and keep moving it toward the casing closer and closer as you have wear, but in effect that moves it farther and farther away from the stuffing box cover. And that's where these back pump out vanes come in. These back pump out vanes are designed to help lower the actual thrust loading of this pump. So the more open area between the impeller and the stuffing box cover, the more thrust loading is on this pump shaft and on this bearing assembly. So if you have extreme clearances, wide open clearances, you could be experiencing thrust bearing failures. Once again, open clearances, extra wear, all have an effect on reliability. Additionally, as this clearance is opened up with the impeller away from the stuffing box cover, not only does it have an effect on thrust loading, but it also doesn't allow for the back pump out vanes to actually push solids and particles outward as this thing is spinning and running. So it's less efficient that way. So it allows for larger particles or solids to get in by the mechanical seal. Lastly, when this clearance is opened up, it also creates a higher stuffing box pressure, which causes your packing to leak more heavily, as well as mechanical seal failure. So we covered this 3196 ANSI pump. Now I'd like to just show a couple other examples. This first example is a Gould's 3175 stuffing box cover. As you can see, there's grooves in here that are marginal. They're probably in that less than an 1/8 inch depth area. So you could, in theory, reuse this thing, but it will have some area of leakage and a little less efficiency. Here we have an impeller that was pulled off of a pump, and this is not the actual impeller to that side plate, but you would look for wear on the face of the impeller as well as these back pump out vanes that we talked about earlier. And then of course the suction side plate. The suction side plate is on a 3175 pump, and as you can see, the grooves are actually fairly deep, and this particular side plate I would not recommend reusing because it will definitely have a fall off on performance and ultimately reliability. And then the third one is a casing. This particular casing was set with standard clearances, and which was like 8 thousandths as we stated earlier. And the actual operating temperature in the process was over 300 degrees. So this impeller was actually set closer to the casing than what the O&M manual recommends. And therefore we had impeller to casing contact. So this has significant wear on it. This next example is a Gould's 3196 XLT pump. Now this particular back pullout assembly that you're looking at here has significant abrasive wear throughout. You can see not only is there wear and irregularities on the works area of the impellers, but on the face that goes against the casing. The back pump out vanes are nearly gone on the back side, and you can see that there's cupping on the stuffing box cover going across from the center outward. Lastly, I would point out that up near the cutwater area in the casing, there's an extreme amount of washout as well. Now this is clearly an abrasive wear example. Okay, so up to this point we talked about really end suction centrifugal pumps. We also have split case pumps. And instead of having an impeller to casing wear ring clearance, we have an impeller wear ring to a casing wear ring clearance that we have to pay attention to. Those are very, very critical, especially on a double suction pump or a split case pump. You're down to a total of 20 to 40 thousandths depending on the size of the pump and the material of the rings we're talking about. But those particular dimensions are really about performance and reliability as well. So to get this to make your pumps last longer, it's very important that when you do a rebuild and you put the expensive bearings and so forth into a rebuild, it's important that you look at all these different areas, the stuffing box, impeller, the casings, all those clearances, how much wear. They will all affect reliability of your pump.
Okay, a couple things to review from Joe's talk. Obviously, the pump performance, the flow, and the pressure, they're affected by the conditions of the liquid end components. But it's also important to note that the flow problems can also cause mechanical problems. These principles apply to all rotating equipment, whether you got agitator, blower, vacuum pump. The mechanical aspects of operation are affected by the process side of the machine. Talk a little bit about impeller balancing. So in the case of pumps, impeller balancing is a critical part of the precision rebuild. So there's common ISO balancing specifications. G6.3 is the standard spec for pumps, but best practices suggest balancing to a higher spec. So some of our customers, they take great pride in their equipment reliability, and they strive to maintain world-class vibration levels. So because of that, we make it our goal to balance to G1.0. It generally doesn't take much more to get to that level. And because of that, why not take advantage of the resultant lower vibration and increased equipment reliability? So we're going to talk a little bit about gearboxes. I'm going to turn things over to Rob for a second here.
Thank you, John. Good morning. I'm Rob Adair. Thanks for joining us today. John's precision repair presentation on pumps translates across the board to all the other equipment that is worked on, such as positive displacement blowers, multi-stage turbine blowers, liquid ring vacuum pumps, and the list goes on and on. Now we're going to give you an overview of what we look for when we tear down and assemble a gear reducer.
Hello, I'm Rob Adair. I'm up at the Grand Rapids location. John's just went through precision rebuilds on pumps. Some of that translates to what we do here, but we have a Falk 1060 right angle gear drive that we'd like to go over. We laid all the parts out, they've been inspected, cleaned, and now it's ready for assembly. On this particular box, we had a cause of failure, a lack of lubrication. The bearings ultimately spun in the housing. This bearing actually welded itself on the race. The lack of lubrication also sent, when the bearing started to fail, a misalignment, and it put wear on both the gears. And then there's a fit where this gear goes on the shaft that's out of tolerance, so we have to replace this shaft. All of the bearings were in tough shape, but we always replace the bearings and seals on a rebuild. Here we cooled the shaft to a specified temperature with liquid nitrogen and heated the gear to specified temperatures in order to facilitate installing the gear onto the shaft. We've partially assembled the output shaft. That consists of 2 Timken tapered roller bearings, a full pack of shims, and we've torqued the bolts, the bearing cover bolts down to a specified value. We're then going to check the axial clearance in the shaft. We're looking to get that to a specified value by removing shims. Once we have the axial shaft clearance set, we'll then remove the correct amount of shims in order to give us a proper preload on the bearings. It's important to get all these values and everything torqued to specifications in order to ensure precision repair. So Todd's going to go ahead and check the bearing clearance with the full shim pack in the bearing cover.
What we're going to do is with the dial indicator, we're going to check axial clearance, which is actually the movement up and down on the shaft to set the clearance of the 2 bearings and the bores. So I'll zero out the dial indicator. To 0. And making sure that the shaft is seated all the way down to the bottom to get the full clearance out of the bearing. So you can usually tap with a dead blow hammer to seat everything down. Then we'll just lift up on the keyway to get my clearance, find out what it is. Sitting at about 10 thou clearance. Now that we've determined what the axial clearance is, manufacturer specs for this shaft has preload on the shaft or for the bearings. So we have 10 thou clearance and we need -3 to 5 thousandths clearance. So removing the shims out of the bottom of the cover, I'll take 10 thou plus the preload, which would be 3 thou. So I would take 13 thou shims out of the bottom of the shim pack in order to get preload on the bearings.
We removed the bearing cover, we removed 2 shims, and now we've reinstalled the bearing cover, torqued back to values, and we're going to recheck our end clearance. Todd's going to do that right now.
Now to check axial clearance again after removing the shims, I'm going to tap and seat the bearing back down to the bottom. 0 with the dial indicator. Pry up on the shaft to getting 3 thou clearance. So my next step to get the preload for the shaft or for the bearings, I'm going to remove 6 more thou shims out of the shim pack to get to my preload. Sorry, John.
Oh, that's fine.
We've assembled the output shaft and set the axial bearing clearance. We now have to set the correct mounting distance, which is done by adding or subtracting shims between the 2 housings here. Once that's complete, we're then going to set the backlash, which will be done through an inspection hole on the side. Once that's complete, we will then, since we have the bluing on here, we'll then do the patterning and make sure we got good gear mesh. We set the correct mounting distance and backlash. We put bluing on the gear to check the patterning to ensure that we're getting proper gear mesh. Everything looks good. We'll now put it back together and send it out for paint. Once the reducer is assembled and final inspections are made, we then send it off to the paint booth. There, it gets the final cleaning, it'll get taped off, and then painted with a either industrial paint or epoxy.
As you can see, a precision repair starts at disassembly and carries through assembly all the way down to prep and paint. We're now going to do a polling question. If your bearings require 3 thou preload and you're currently at 6 thou end play, how many thousandths of shims must be removed? Okay, it looks like everybody's in. For the most part, you put 9 thou down, and that is correct. You have to remove 6 thou to remove the end play, and then another 3 thou in order to get your preload. And now that's all I have for you. We'll go to Q&A.
All right, guys. Well done. We appreciate it. We do have a few questions that came in. For anybody else who has questions and has not yet had a chance to enter those in the questions box, please go ahead and do so. Also, before we get into the questions, just another quick reminder to please take a minute or two to complete the survey once we end the session. And again, if you don't have time at this time, a survey will be sent via email within 24 hours. So we would definitely appreciate you taking the time to fill that out. All right, Rob and John, we've got a few questions that came in. The first one here, if a bearing housing fit, I think they're talking about the bearing fit. So if a bearing housing fit is 3 10,000ths out of spec, is that big of an issue? Or would you be okay reusing that?
I guess for a precision repair, we'd say no. You know, like Nate said during his shaft inspection, he said, out is out. You know, if you're 0.3 of a thousandths out of spec for 1,000ths total tolerance, you're 30% out of spec. And, you know, you have to look at things too. You know, that outer race of the bearing is meant, you don't want slippage in the bearing housing. And it's pretty critical. And a lot of that is, you know, engineered into the design, knowing that that bearing is going to expand a little bit, and then it should become tight in the housing. And so if you just, you know, these are tight tolerance things, bearings are tight tolerances, so you need to hold that bearing housing to a tight tolerance.
All right, thank you, John. Rob, this may be a good one for you. What is the most common or #1 cause of premature gearbox failures?
Based off our experience, it would be bearing failure based off of lack of lubrication. Whether that be improper PM maintenance, it's important to make sure that you use the correct oil and follow the correct maintenance practices on them.
All right, thanks, Rob. We've got one here on packing. So if I'm using packing instead of a mechanical seal, is it okay to relax some of the precision criteria that was covered throughout the assembly process in this presentation?
Well, I'd say maybe a little bit. I think we would still hold to some of the critical, like the bearing fits, oil seal landing areas and repairs on that. I think like in the case of the shaft that Nate was looking at, so that shaft was probably borderline, you know, is close to 2,000ths run out on that shaft. And then we also had some corrosion issues in the packing area or where the shaft sleeve would seat. You know, if it's borderline like that, I'd say for mechanical seal, we'd say it's not good. But if it was packing, you know, we could maybe relax a little bit on some of those details, but we'd still want that shaft to spin correctly. We'd want bearing fits to be right. So, you know, a little bit, but it's usually a judgment call depending on the condition of the shaft generally.
All right, thanks, John. We've got a few more here. Do you need to make adjustments to a mechanical seal when setting the impeller clearance?
Well, you know, the mechanical seal clips need to be installed, and you know, generally that mechanical seal, you put the clips in, reset the clearance, and then reset the mechanical seal.
So what are those, the clips you're referring to, what are those doing when you install those in the mechanical seal?
Well, basically you're releasing the mechanical seal from the shaft. Sometimes this does cause problems because maybe an O-ring is already seated on the shaft, but you're basically releasing that mechanical seal from the shaft. You're putting mechanical seal clips in to basically hold that mechanical seal in its proper position. Then you would reset the impeller clearance and then reset the seal.
Okay. So it's important to have those in to make sure you're not changing the compression,
Yep.
or, you know, the force, either too much or not enough on the seal bases as you're rotating assembly, adjusting that impeller clearance.
Right.
Perfect. Thank you, John. With lift station pumps, would you be looking for the same information? So I think what they're saying there probably is, would you be following the same criteria for pumps that you would typically find in a lift station?
Yeah. Yes, absolutely. Yeah.
All right. Here's one on bearings and lubrication, specifically grease. So how do you determine how much grease to add to a bearing?
Well, that could be a pretty involved answer. You know, there's definitely steps to be when you're packing a bearing. Well, I don't know. Could be a lot of different ways to answer that question.
Yeah, typically referring back to the IOM or consulting with the OEM and getting their recommendation is best practice. But yeah, there are a lot of variables to consider, certainly. But the person that asked the question also made the point that adding too much grease can be just as bad. In some cases, not having enough can cause the bearings to skid and not operate correctly.
Yep, absolutely.
So, okay. All right, that's all we have for questions, I believe. So with that, we'll go ahead and wrap things up. Again, we appreciate everybody attending and participating in our training session this morning. One last reminder on the survey that should pop up as soon as we close out of the session. And Rob and John, we appreciate you guys hopefully sharing some tips and tricks that'll help our customers improve the reliability of the rotating equipment. So with that, everybody have a great and a good weekend, and talk to you later.